Have you ever been stuck in traffic only for it to suddenly clear? With nothing there? No crash, no cones, just a jam that somehow formed.
In a utopian world, traffic should work like a perfect machine, everything moving in sync. But one distraction, one mistake, and the whole system slows or stops.
So when millions of split-second human decisions collide at high speed, what happens? What causes traffic, and how do designers work to save the hours lost waiting around? To solve such problems, people created traffic management systems.
For traffic.
By definition, traffic management systems are solutions that use sensors, lights, signage, and data analysis to predict traffic on roads, optimize traffic flow, and reduce commute time. Although traffic cameras, signals, and speed detectors are present to manage traffic, we see congestions every day. In practice, governments use a combination of road infrastructure and technology to optimize traffic flow, especially in high congestion areas and peak times. The goal of traffic management systems is simple: reduce or even eliminate traffic congestion and ultimately shorten commute times.
According to the Federal Highway Administration, about 45% of congestion is recurring, built into bottlenecks and everyday choke points inherent to the roads. The other 55% is non-recurring: crashes, bad weather, construction zones, and special events, plus random human behavior that interrupts a road's natural flow.
Same road, but the effective capacity changes minute to minute.
In the early days of transport, the road network wasn't just built for commuting. Military and wartime logistics during the World War II era demanded fast, reliable movement across huge distances. In 1956, President Eisenhower signed the Federal Highway Act by investing $25 billion to construct 41,000 miles of interstate highway system. This created a massive boost for an economy that runs on wheels and is on demand.
And once driving got easier, demand exploded, which brings us to how we fight the jam.
The structural design of roadways makes up about half of the source of roadway traffic. Engineers try to improve a roadway's capacity by adding more lanes and more roads, but those plans are foiled by Braess paradox.
In some networks, adding a lane can actually make everyone's travel time slower because drivers all pile into the same best path. So clever design approaches help to effectively maintain a road's capacity when demand is up.
Roundabouts are used all around the world to replace the congested four-way stop, cleverly keeping a constant flow of traffic. That way cars don't pile up waiting for their turn.
The diverging diamond interchange helps maintain flow by reducing stoplight times and turn lanes, making the volume of traffic the road can handle much higher.
But more infrastructure isn't always possible. Inherently, roads have a limit to the amount of traffic they can handle. Luckily, planners and civil engineers can manage a road's demand by adding HOV lanes or toll roads to remove the volume from the peak. For unpredictable events like emergencies, these solutions are different.
Smart systems like adaptive signaling dynamically adjust green light durations by analyzing the upstream traffic volume and real-time arrival predictions. By reacting to the actual number of cars waiting rather than a fixed timer, these systems can reduce wait times by 15 to 20%. Another smart traffic management system is the navigation app on your smartphone. It is a part of traffic management now and helps to control traffic.
It can find hidden capacity, but it can also push too many cars onto small streets, creating new bottlenecks.
And when driving feels more predictable, more people choose to drive. So demand rises to meet the convenience. To counter this, governments invest in public transport. High-capacity alternatives like the light rail, express buses, and even protected bike lanes are some alternatives to driving.
Cars are getting smarter too. Automatic braking and smart cruise control can smooth the tiny mistakes that start waves.
And connected vehicles can warn you about hard braking ahead, or even share signal timing, lane closures, and work zone alerts. Why does any of this matter? Congestion can lead to injury or death, a wrecked car, and lost time on a national scale.
The Travel Time Index, or TTI, is a measure of a road's efficiency. It compares travel time at a road's peak to when there is no traffic at all.
In major metros, peak trips can take about 20 to 30% longer than they should, and over a year, that can become dozens of hours per driver.
It affects productivity, shipping, and safety, especially when roads turn into constant weaving and stop and go. In the United States, this equates to an annual loss of $86 billion in productivity and 40 to 60 hours per driver.
But couldn't this all be solved if we had complete control of the system? That's the promise of network signal timing with help from AI, connected infrastructure, and eventually autonomous vehicles. Fewer shockwaves, smoother merges, tighter spacing. This means less accidents and traffic on the roads.
But the cost isn't just hardware. It's data, cybersecurity, and big choices about how much control we're willing to hand over. When we become destination setters instead of just drivers, we could be giving up our decision-making power to others. Luckily, the power is in our hands more than we think.
In the sci-fi version of traffic management systems, every merge is negotiated in the cloud, and every trip leaves a trail. Here's the takeaway. Traffic management can smooth the flow, but it can't override the fundamental balance of capacity versus demand.
Even with self-driving cars, high demand is still high demand.
The real win is a smarter system and smarter habits.
So leave space, drive smoothly, and you might stop the next phantom jam before it starts.